go to the sharing mode. Open share tray. So this is it. So it's on record. Yeah. So we'll go to thermodynamic system. Okay. So we have L. Yeah. So what we'll do today is get into little mathematical forms of things. So now we have identified thermodynamic systems, or you build a base for how what would be thermodynamic coordinates and all that. And when you put together all the coordinates, you get a system, or actually the other way around. When you want to consider a thermodynamic system, that has to be defined by a bunch of coordinates, which are thermodynamic coordinates, which in a way can be thought of as some of the variables in a normal coordinate system, and 2D representation or 3D representation. Like for 3D you have 3 coordinates, 2D you have 2 coordinates. That's on a graphical thing that you do. But all of those things we can put in a thermodynamic system with thermodynamic coordinates, depending on how many variables you have. And then when we try to define a system in a mathematical representation, then we should give the thermodynamic coordinates a mathematical form. Okay, the thermodynamic variables we'll have to do in a mathematical form. And what do we generally do by putting a mathematical form? It's a representation of something happening, some physical system. You want to represent it mathematically, and you want to see the changes, because eventually you want to understand a system, meaning that the system is dependent on so many other variables, and you like to understand how subtle changes in each of these variables bring about change in the whole system, right? That's the reason we want to see the influence of these variables on the thermodynamic system. And when we do that, we see subtle changes in each of these variables, and the sum total of these variables, or the changes of these variables, actually bring about the overall change in the system. That's why we use a term. You might have seen things in your 10+2. We see for a small change in volume, we write dV. For a small change in distance, we write ds, or things like that. What do we mean by that? That simply means, I think it's very trivial, but then I should put it clear, is that when we see when we say a change dV, okay, that is something which is much smaller than the macroscopic changes. If you compare the macroscopic changes that you see or perceive, okay, it is much smaller than that. But then it's also much larger than the atomic scale dimensions. It's somewhere in between. So when you say dV, I'm not trying to say that what is the change in volume of a nitrogen molecule. No. Or the apparent volume of a nitrogen molecule at a certain temperature, because you really don't think that a nitrogen molecule would change in its volume, but it's a perceived volume. It's at certain temperature, the kind of volume it occupies with its vibrations and things like that. That's the overall volume of that nitrogen molecule, or any other molecule for that matter. But when we say dV, it's much larger than what is happening in the atomic scale, but at the same time it is much smaller than what is happening in a gross scale, in a bulk scale. Okay, it's somewhere in between, and those small changes we kind of integrate over to find out the bigger change, the whole change. That's just a trivial thing, but then I thought I should make it clear. So it's a simple thing. A function is dependent on the variables x and y, as it is said. It's f is f of x and y. It means this is the function f is influenced by changes in x and y. And these are representations only. X and y can be anything else, and f can be your chosen thermodynamic property that you want to see. or it could represent the whole system of what is happening. And for this small changes, what is happening is that the variables, these are the variables here, it concurrently these things change. Concurrently x changes and y also changes in the movement, and the overall effect of the changes is influenced here. But then if you like to understand what's happening there, it's kind of easy to understand with the change in the function f with only the variation of x. Okay. Likewise, you want to see the change in f with only the variation of y. That becomes much simpler, Rather than changing all the things all at a time, what we do in a mathematical process or mathematical way of understanding things is that we keep everything else constant. We change one variable and see what is the effect of it. And we go to the next variable, change that variable while keeping the other variables constant and see what's the change in it. And when you put together all of those things, you see the overall change in the thermodynamic system or the function f. So that's what is written here. df is the partial. This is what we represent by partial derivatives. Partial f by partial x multiplied by dx when y is kept constant, plus partial f by partial y while x is kept constant multiplied by dy. And that's in a way is represented here. The shaded area, the colored area is a surface, sort of representation of a function. And that function can be some x cube, ax cube plus by square and things like that. Now it's not a simple plane, it's a curved plane, it's sort of a surface. And that surface, you want to change with the, what is the change with x when you what do you mean by change in x? Meaning you want to go across like in this direction to x and see what is happening with the plane, and you want to change y, and then you want to see what's happening with this plane. So according to this equation, what we do is we keep the first one, we keep y is x. Y is constant. That means if you want to keep y is constant, that means this is y. So this is a point here, which is, if you go like this, if you change x without changing y, it'll be somewhat like this. Okay, that means this representation on this surface is this line. All right, and we want to see del f by del x. That means the change in f with the change in x. That's what we're trying to see here. This is the slope here. This is the slope here. We want to see del f by del x here. Okay, and that is at a y constant. Likewise, we want to see what are the functional changes with x kept constant. So x is this is x, and then we want to pick a point here x, and with x constant, if y changing, that means in this line y changing like this, which is this plane. Okay, and this plane is intersecting this curve, this y function surface on this line, and this point you want to see del f by del y is x. This is a generic representation of things. Instead of x, you can put any other x and y. You can put basic variables like volume, temperature, and things like that. And instead of f, you can put any other higher thermodynamic parameter which you want to study. All right, so that's a simple representation of things. So again, we sort of from a generic perspective to putting our common variables into these equations, you could write like this, what is given in this slide, where our most common variables in thermodynamic systems are going to be temperature, pressure, and volume, where instead of talking about a higher thermodynamic parameter, we are talking about the overall changes here in all of these parameters, in the change in one of these parameters as a function of the other two, temperature and pressure. You can simply write as this is written, V is a function of T and P, and so you like to find out the change in V as a function of changes in T and P, you can write simply this: dV is del V by del T at constant pressure into dt plus del V by del P at constant temperature into dP. So it's as simple as what was written there. And likewise, you can swap things in the sense that we want to see the changes in T, okay, with the changes in P and V, or you want to see the changes in pressure with the changes in temperature and volume, can be respectively written as here what is given here dt, where you keep a volume constant and see the temperature change with pressure change, plus you want to keep the pressure constant and see the change in temperature with change in volume multiplied by dV, like that. So these are the basic representation of thermodynamic variables, and all of these variables and the changes put together give the overall change in the required thermodynamic parameter. So these are simple mathematical representations. I hope you're comfortable with this. Okay. Now we come to an Euler chain relation, which is kind of important when you're going to be solving bigger thermodynamic identities and trying to relate between higher thermodynamic properties. Higher thermodynamic properties, I mean, which are a little complex in nature. I mean, when we say those things complex in nature, I see the simplest ones are temperature, volume, pressure, and composition, and some of the parameters like that. But when you talk about other things we haven't talked yet, like internal energy, work, enthalpy, entropy, specific heat, these are the higher thermodynamic parameters. It's a loose term, but then I think you understand what I want to say. So when we try to fix or establish relationships in different boundary conditions between some of those higher thermodynamic parameters, sometimes we would be using this Euler chain reaction. It has a derivation which comes from differential equations, but a simple one, but I haven't put it here. It's kind of easy to understand, easy to remember, so to speak. So this says like this: if f is a function of x, y, z, which are three thermodynamic variables, or variables you'd say. For us here, it's thermodynamic variables. Otherwise, they are simple. Then what you do is you write del x by del y at constant z, del y by del z at constant x, and del z by del x at constant y. All of those things multiplied gives you they give you -1. And we want to put all those things in the PV in T space. You simply write like this: del P by del V at constant temperature, multiplied by del V by del T at constant pressure, multiplied by del T by del P at constant volume, would give you -1. That we'll see how it's sort of changed and applied in subsequent classes. Now let's see. It's a simple shift of our focus, in the sense that we want to see physical systems, bulk physical properties, and can we represent some of those physical properties in terms of mathematics that we have taught recently. These are three basic functions that I've written, and you must be familiar with these. Say the coefficient of thermal expansion, alpha, bulk modulus, and of course the compressibility factor, or compressibility coefficient. Okay. Now let's talk about coefficient of thermal expansion. You always know about this, but I think you guys might have been familiar with the linear coefficient of thermal expansion, where you see the changes in the length of a wire or a rod as a function of temperature, but that generally comes from the overall term, which is the volumetric coefficient of thermal expansion. We also represent that as alpha. Rather, we see that we also represent coefficient of linear thermal expansion. We represent that as alpha too. But then, just to make it clear, we have written as alpha V. So here, what is happening? The effect of temperature on volume of any solid would be that when you increase the temperature, the volume of the solid increases. It's kind of true for the gases as well, but we are not talking about gases here. We're talking about typically condensed matter, typically solids, metals, ceramics, or polymers, or anything of that sort. That's where coefficient of thermal expansion is useful. So you want to see what's the change in volume of that solid or the substance of interest with the increase in temperature, and you want to standardize it. You want to find out a metric for that, and that metric is alpha. What you do is you had at some temperature you had volume, and then you increase the temperature uh, slightly, and then you observe what is the change in the volume, and you want to see the change in volume divided by the change in temperature, which is simply written as del V by del T. And although it might seem trivial that you don't have to put you don't have to put it partial, but then that's fine. You don't have to put a partial because that system is so simple a system. But then the condition is that you have to keep pressure constant, which is what is happening. It's a rod, a metallic rod, and if I heat it up here, and then you want to see what is the change in this rod with the change in temperature, you might see that the pressure is kept constant here. All right, it seems simple, but then just to be perfect on the writing part, we've written here the pressure is kept constant, and that's why it has to be represented in a partial format. All right. So this change parameters that has to be normalized by the overall volume, because that's the deal. It's like what's the change divided by the original thing. Change in volume divided by the original volume. That's what is written here. So this you can also write it for a linear coefficient of thermal expansion. Instead of V, you got to write the simply length. So change in the length of the body with the change in temperature, while pressure is kept constant, normalized by the original, the standard original length. So that would give you the coefficient of thermal expansion. Likewise, you want to find out the bulk modulus. You got to go back and read what's bulk modulus. And it's a change in pressure with a change in volume. What's the change in pressure with the change in volume? Okay. Actually, we should have talked about this first, the compressibility coefficient. All right. It's sort of very easy to understand. Compressibility. All right. I mean, how well or how easy or how difficult a substance is to compress. And how do you compress? You compress by putting forces, right? You want to squeeze something, you want to press it down and decrease its volume, right? So what's the change in the volume of the body with the application of pressure? As with if I hold it like this and then I want to put pressure onto it. All right. So what's the change in volume with the change in pressure? Like we did here, what's the change in volume with the change in temperature? Like here, what's the change in volume with the change in pressure, while temperature is kept constant. We are not sort of changing temperature, keeping the temperature constant, and that's the reason for isothermal compressibility, right? So the change in volume normalized by the change in pressure at constant temperature, the overall change thing normalized by the original volume would give you the compressibility coefficient. Right? And why is the negative here? The negative here is because you want to put a pressure and the volume, the change volume is actually lower than the original volume. You want to compress things, so the delta is always a negative quantity. All right, and that's why there is a negative sign here. And you just for different ways of representation of things, compressibility factor or compressibility coefficient, take a reciprocal of that becomes the isothermal bulk modulus, or written as B or some kind of a Latin B. That's what's written to represent the bulk modulus, and that is simply the reciprocal of compressibility coefficient, which is like minus V multiplied by del P by del V at constant temperature. These two are isothermal quantities, isothermal thermodynamic properties, whereas this one is an isobaric situation. So likewise, many different thermodynamic, many different physical properties can be explained or can be represented in the thermodynamic way, right? We can look at some of those things. Like what's the case of a stretched wire? You might be wondering that we're supposed to be learning about heat and thermodynamics and some things like that, but why are we reading about physical properties? That is precisely the point. The point I want to bring in here is that when we talk about solids, we talk about we're actually reading materials thermodynamics, thermodynamics of solids, and you as materials engineers, we must understand, we must be able to apply thermodynamic principles to solids, and not simply the temperature behavior like melting or crystallization or amorphous to glass transition and things like that, but in normal temperatures also there are innumerable systems, innumerable physical properties that can be explained with the laws of thermodynamics. That's the point I want to bring in here. And that the concept of energy and work and everything that we're going to be discussing further in different sections. From the very beginning itself, I want to make you open to the interpretation that thermodynamics is not just about heat. In general, it's about energy, and when energy is involved, you can put a thermodynamic system into it, and you can apply thermodynamic principles to understand and predict what is happening in the system. So, like the case of a stretched wire, you might have done experiments in your 10 plus 2. You sort of hang a wire and then put a weight on that, and then you try to figure out what's something called the Young's modulus. All right, that's what is written here. Young's modulus. You might have seen the loading and displacement kind of curve, where we're talking about the linear section of the load displacement curve. Here, Young's modulus is defined by the pressure divided by the change in length in a system, and that if you put here, the pressure is the tension by the cross section of the wire, that is F by A, which is the pressure, and then the change in length, which is we write as del L by L or something, which is sort of reorganized here, is written as L by A. L is the length, A is the area of the cross section. Area is nothing but the cross sectional area, and then the change in the tension, the force, normalized by the change in length. You apply a force, you change in length, and that is being conducted at a constant temperature. But the slight twist here is that, which is exactly what can happen when we talk about the changing of different variables and its effect on the overall property, is what is given here. So we are talking about change in length here with the application of a force, which is what Young's modulus is talking about. All right. On the other hand, look at something called the change in length because of the change in temperature. All right. So that's what is called the linear coefficient of thermal expansion, which is del L by del T normalized by the original length. While we have to assume here that force is constant. There's no additional force acting on the wire when we try to measure the linear coefficient of thermal expansion. We got to think that F is sort of constant. All right. So here are two cases here. When T is constant, you are defining change in length here. Okay. When F is constant, we are also defining change in length here. All right. And then we have to apply the Euler formula to figure out the connect between these two parameters. Here the temperature was kept constant when you're trying to see change in length with change in tension, and here the tension is constant. We're trying to sort of find out the change in length with the change in temperature, and is there a connect between these two parameters which were kept constant? If you go back to Euler's relationship, so this one, and based from this, you should be able to calculate the change in these two parameters, del F by del T, while the other parameter length is kept constant. All right, we have three variables here. F is the tension, T is temperature, and L is the length. So we had different formulations for these two while T and F were kept constant. Now you can keep L constant and find out del F by del T, which is, this kind of a situation where this is area into Young's modulus into alpha. Alpha is the linear coefficient of thermal expansion. So that this relationship gives you a clue to understand the change in force. What's change in force? What's change in tension with the change in temperature? Right, and do you really need to keep the temperature constant while you're doing experiments of Young's modulus? That is something we can figure out. And then, for a particular system, let's say steel wire. Okay, take a steel wire, and then you know the Young's modulus of steel, from data, from people with this. This is one of the most tried experiments. You try to figure out what is the type of steel that you've taken and what's the Young's modulus of that. And you consider a particular wire, for a 0.5 millimeter diameter cross-section wire or a bigger wire or things like that. And also from the tables, look up what is the alpha, the coefficient of thermal expansion. And then you multiply all of those things and then see a number if that is significant enough to see that would there be a change in the tension with a change in temperature. All right, so let's say, and how can we use it? We are talking about some application here. Like you have some engineering sort of design, or you made some system, some machine where you have to sort of put a weight through a steel wire of certain dimension of cross section. And while you do experiments or while you do your work with that machine, there is a change in temperature. I mean, from normal temperatures, let's say 25 degrees Celsius, or let's say 45 degrees Celsius in the summer, to almost 4 degrees to 5 degrees Celsius in winter, like for example, the case in Rourkela. So there's a 40 degrees Celsius change in temperature. All right. So is your system able enough to work as precisely as it was in 4 degrees Celsius vis-a-vis as it is in 45 degrees Celsius? And that would give you a clue if there is, if you find out if there is a change in tension with a change in temperature, with the change in temperature about 40, and is these number a significant number enough? So that kind of would give you an idea. This is some random example I'm giving you just to establish that the tension and the change in tension, the change in temperature, can it be a significant one or not? Should you really bother about that or not? That would depend on this number and the calculation of this number. But the fact that you are able to calculate these functional changes in any of these variables that is happening. All right. Now, likewise, we're continuing to discuss some other physical systems. We talked about the case of a stretched wire. Now we can talk about other things as well, which you might have seen, might have experienced. Like talk about surfaces. Talk about surfaces. When you talk about surfaces, there are so many examples of surfaces and then how does it work. But one example could be that of a soap bubble. You put a soap bubble, so working with detergent, you could see that your froth formation is there and you have the big bubbles are forming, and then or you sort of आपने तो ये क्या होगा ना, वो जो बच्चे जो करते हैं ना, you dip your wire frame in soap solution and take it out and then you blow, right? So what do you do? That there's a soap film in the wire frame, and then you're trying to push air through it, or actually you're putting pressure. In a way, you're trying to increase the area, right? Okay, so that the surface, the soap film has a tension, and you're trying to increase the area. It's not the volume thing. You're trying to increase the area. That is one kind that you're doing, and you can think of it as a thermodynamic system. We'll come to more on that. What is the important parameter there that you need to be worried about, right? Likewise, talk about an electrochemical cell. There's so many different kinds of electrochemical cells, right? The Daniell cell is just one example. You can take many such examples here. Right? The Daniel cell is what? It's a rechargeable cell, where on the normal discharge mode, you eat up zinc with the copper sulfate solution and then sort of deposit copper at one electrode, right? And the reaction gives you a volume sort of potential change of 1.1 volt. And this potential change that gives you some charges. So you kind of collect the current because of the potential challenge, the current flows, and you tap the current, and that you sort of make useful work out of that system. So here, the point I want to bring in is that the potential has some connect with charges, right? Likewise, talk about a dielectric slab. I don't know, you guys might have seen dielectrics or capacitors and things like that. Pele, when the tubes were there and the tubes are not able to light up, and then you put some, कोई आता था ना वो डाइलेक्ट्रिक एक कैपेसिटर लगा के it used to make the tube glow steadily after that, right? So likewise, those typical big type capacitors have gone. Now you have highly sophisticated capacitors come to the market, and they're easily available, in the marketplace. Well, what's the idea? The idea is that you put an electric field, and that electric field induces electric dipoles, to orient in a particular fashion. So I would like to think of it as a cause and effect kind of thing. Cause and effect. That's what I want to bring you into. The cause is the electric field, and the effect is the alignment of the dipoles in a particular direction. Okay. Likewise, you have magnetic things like that. You apply a magnetic field, and then the magnetic dipoles in a body preferentially get aligned to a particular direction. It's magnetic alignment. The domains that you have in a body, like soft magnets and hard magnets that you'll study in higher classes. That's also one kind of a physical thermodynamic system where the cause is the magnetic field and the effect is the alignment of magnetic dipoles. So here in the next slide, I made a list of some of these intensive and extensive coordinates, and I would like you to think really deep, going away from typical pressure volume system. This is the hydrostatic system that we always talk about when you talk about thermodynamics. Pressure, volume, number of moles, and work, and internal energy, and things like that. That's fine, because that's a base system. We start from there. That's the hydrostatic system that we say. Right. And here you see where we are leading, where we are going at, is that this is the cause and this is the effect. Okay. Like the case of like this, we have the stretched wire system where there is tension, and the tension is associated with length. The tension, and then there's the change in length and things like that, right? Like for the surface case, surface of a soap bubble, or surface of catalyst, which is used in chemical reactors in petroleum industries, or another tools. Used in chemical reactors, or used in particulate systems, used in adsorption, even in batteries in different aspects. So there's a surface tension, and there's this area, surface tension, gamma and A. Likewise, you have the electrochemical cell or batteries and all that. You have electromotive force, which is, I should have written here V instead of E, because E has got another thing. I hope you understand that. Electromotive force, typically the potential, and then that it's connected with the charges, the flow of charges that can happen in an electrochemical cell. Likewise, you have a dielectric slab, with electric field that induces polarization. That's electric dipoles within the body. Likewise, you have a paramagnetic substance where magnetic field aligns magnetic domains, sort of magnetizes the body, um, and that's kind of the effect. This is the cause. This is the effect. And magnetics. This is the cause. This is the effect. See, all of these things put together. What's the commonality here? That's the best thing to think about. That there is a commonality. The commonality is that what is it, or the common thing with pressure and volume. All right, I want you to think hard. Okay. And of course, yeah, one point I'm missing out is that the first the middle column here, these are the systems, and these are the coordinate pairs. I would like to call it conjugate systems, conjugate coordinates. What is its pressure and volume? When it's multiplied, what does it give you? Anyone? You can keep your sort of unmute and speak. Yeah. What is the connect between pressure and volume? And you see that one is an intensive coordinate and the other one is an extensive coordinate. I think it's very important for you to sort of understand and then put it into perspective. That's what is it, the set of things, and that give you distinct property. All right. So if you look at it, pressure and volume, that gives you something called work, which we define as PDV. We'll deal with that in subsequent classes. Pressure and volume is the work. All right. The point I was trying to bring in all this while is that all of these things can be work. F, dl, gamma, dA. What's a work equivalent? You can find out from the voltage difference with charge, electric field, and polarization. It's not simple linear relationship. There's a little bit of a fudging you got to do with the permeability and things like that. And of course, magnetic field and magnetization. So when we go into studying the conservation of energy in the domain, in the discussions of the first law of thermodynamics, I think you've read it at some point somewhere in your 10+2. I think the law is not that it is unknown to you. But the additional thing that I want you to think about is that when we talk about work, we're not always talking about a pressure volume work. We're not always talking about a hydrostatic system. All right. This can be very generic. This can be, into anything that you as material scientists or materials engineers would be doing, be it electrochemical work or, talking about work in magnetic substances or dielectric substances, or talking about surfaces, anything for that matter. All of these things can be clubbed, can be thought of in the domains of work. And, as an engineer, you would like to maximize work. That's another thing that we'll talk about in the next class, as to how, what's the objective in studying the first law is to understand work and maximize work. That's the difference between, just studying and then, heat and the internal energy and work. That's the basic study. But then the approach should be in the whole domain of first law, how to maximize work. Okay. So we'll leave it for the next class. We'll stop it here and see if there are questions to take. Right? Let me stop the recording. Okay.